The Internet is evolving to carry a much broader range of traffic than has been traditionally available, in particular multimedia services such as real-time audio and video. Multicasting is a method for distributing traffic to multiple destinations without sending a separate copy to each one. The multicast routing protocol uses a minimal spanning tree algorithm to provide the most efficient global distribution. Production Internet routers are only now beginning to support native multicast. Researchers within the Internet community developed and initially deployed the M-bone, or multicast backbone, to provide interim support using virtual logical links, or tunnels, that cross over non-multicast capable infrastructure. Internet congestion has increased the incentive to tune tunnel placement to provide the most efficient distribution topology. Tunnel placement should match the structure of the existing unicast topology whenever possible, and ideally travel along uncongested links that carry no other tunnels. We present a 3D visualization of M-bone connections from a list of M-bone links collated by the University of Cambridge MR-Watch utility. We have developed a set of tools to convert the MR-Watch data into a geographical representation of the tunnels as arcs on a globe. The interactive 3D maps use the VRML file format, which allows the graphical representation of each tunnel to contain a hyperlink to textual information about that tunnel. In this video, we are using GeomView, a 3D viewer developed at the Geometry Center that supports on-the-fly color, line width, and grouping changes, but any standard VRML browser will support interactive navigation. This visualization highlights in white the few links participating in PIM, a more advanced but still not operationally stable multicast routing protocol. Here we see the initial deployment of native multicast in the operational Internet, although it does not include PIM being used at sites behind firewalls. Here we classify by domain status. Both endpoints of the black tunnels belong to an Internet Service Provider, or ISP. One endpoint of the magenta tunnels belongs to an ISP backbone. And the beige tunnels are those for whom neither end belongs to an ISP. In this view, we first show only tunnels for which at least one endpoint host belongs to one of the major backbones. MCI in red, SprintLink in cyan, NASA in green, ESNet in yellow, DartNet in magenta, BBN Planet in violet, and ANS in white. We now draw all other tunnels in black. We see that although there are many tunnels between the east and west coast, each provider, when taken alone, has an appropriate amount of redundancy. However, regions with more centralized control and limited network resources, such as Europe, exhibit a far more regular hierarchy and better distribution efficiency. We have been looking at a snapshot of the M-bone from June 15, 1996. We now show data from 4 months earlier, on February 12th, where the SprintLink tunnels are colored in white. We see that Texas A&M University had configured a tunnel to a Sprint machine in Washington, D.C. Notice that in June, Sprint has extended their tunnel support to a major hub in Fort Worth, Texas, but the university has not leveraged the new topology and still uses the now suboptimal Texas to DC tunnel. Although the raw tunnel data is publicly available, the 3D visualization provides critical insight into its nature. In fact, when our collaborator involved with Emblem deployment saw the initial 3D visualization in February, he was inspired to encourage many maintainers of suboptimal tunnels to improve their configuration. We show 700 of the 4,400 tunnels in the dataset. We eliminated 3,200 co-located tunnels and were unable to find geographic positions for the few hundred remaining. The biggest challenge of this visualization was determining the coordinates for each tunnel endpoint. We have had to painstakingly construct a database mapping host addresses to geographic latitude and longitudes, using a variety of methods: the Internet database, trace routes, network maps, web searches, and personal communication. There are several possible future directions for this work. We would most like to map out the underlying unicast framework, but that would require a broader set of visualization and data collection techniques. These tools could also facilitate mapping out other logical components of Internet topology, such as for the deployment of IPv6, which will also involve a tunnel-based transition. Demonstrating the utility of such tools may encourage ISPs and other large networks to make available geographic, topological, and possibly even performance information for use in visualizations that would facilitate Internet engineering on large and small scales.